Hi students, here you are going to start with the new module, the third module, and the first chapter in third module you are going to learn is the differential entropy. Okay, so what is differential entropy? Basically, as a general definition, we are using differential entropy to define the entropy of a continuous time signals. Okay, in the previous videos you have been learning about the entropies of a discrete sources or discrete messages. So here we are going to apply the entropy of a continuous time signals. Okay, but most importantly what you need to understand is you need to understand the difference between the differential entropy and an ordinary entropy. You need to understand the difference between the differential entropy and a normal entropy, or you need to understand why this entropy is called as a differential entropy. This is where you need to understand about this topic. Okay, so first we know that for a discrete messages we define the entropy as h of x is equal to sigma k is equal to 1 to q pk log of 1 by pk. This is the equation you have been always be using to define for discrete sources, right? Where this q represents the total number of messages and this pk represents the probability of any message sk, right? This is one thing you have always learned in the previous classes. Okay, so what I'm going to do is that I'm going to apply my continuous time concept in this equation. Okay, so to apply this continuous time concept, what I need to do is you need to understand two things about this: how to apply this equation for a continuous time signals. Okay, so for that what you're going to do is that, since here I already told you that this discrete messages, that is the number of messages are discrete, which means you can count with your fingers, right? So these are the number of messages that are all discrete in nature, and the limit is up to q, that is q is the total number of messages. So what I'm going to do is that I'm going to take another source. Okay, I'm going to take another discrete source, and this discrete source has infinite number of values. Okay, has infinite number of discrete messages. Okay, and that gap between 2 points, that gap between two discrete messages, I am going to represent as del xk. So which means if that gap becomes zero, I am converting a discrete random variable into a continuous random variable. That is what I'm going to do over here. That is, let x be a continuous random variable source, which is nothing but a limiting form of limit del xk tends to 0, where del xk is the space between two sample points, okay, of a discrete random variable that assumes discrete values, infinite discrete values, that is from minus infinity it goes on to 0, it goes to minus 5 del x, minus 4 del x, minus 3 del x, minus 2 del x, minus del x, 0 del x, 2 del x, 3 del x, 4 del x, 5 del x, up to infinite. It goes on and on. So this is basically a discrete random variable consisting of infinite number of discrete messages. Okay, and if I apply the limit as del xk tends to 0, I'm basically converting this discrete source into a continuous source x. That is one thing you need to understand. Okay, so therefore let k del x, where k is an integer, can be any one of these integers. Okay, so let k del x is equal to xk, which means I am naming each of these as my sample point. Okay, so therefore, which means that minus 3 del x is x of minus 3, minus 2 del x is x of minus 2, minus del x is x of minus 1, and 0 is basically 0 itself. Del x is k x1, 2 del x is x2, 3 del x is x3, and so on. Which means I'm basically applying each of these, I'm naming each of these gaps or each of these space as a single point, as a single sample point. And in that case, okay, if this is one sample point, then the next sample point, the number that comes after this, that is represented by k plus 1. Okay, so the k plus 1 del x, I am calling it as x of k plus 1. So therefore, k del x is xk and k plus 1 del x is x of k plus 1, xk plus 1. Okay, so now I want to find the gap between this number and this number. I want to find the gap between two consecutive sample points. Two consecutive sample points. So what is the space between two sample points? We just need to find the difference between them, right? So therefore del xk is equal to xk plus 1 minus xk. But we all know that xk plus 1 is k plus 1 into del x, and xk is nothing but k into del x. So which means if I apply del x inside the bracket, this will become k del x plus del x minus k del x. These two terms will cancel each other. Therefore we'll get del xk is equal to del x, which means, in other words, each of these sample points that you see over here is nothing but the sample space between any two between any two points, which means you can consider those very same points as your sample space and vice versa. That's what this equation means. Okay, so which means even if you write del of xk or whether you write del of x, both are correct. That's what this equation means. Okay, so that is one thing you need to understand. All right, that is this value, if this value tends to become 0, if this del x or del of xk or del x, when this value becomes 0, then I am converting this discrete random variable into a continuous random variable. Okay, that is one thing I'm going to do. The second thing is the probability. You can see that there is a probability over here. So how would you define the probability of a continuous random variable? You need what you call as the probability density function, or PDF. Okay, so we all know that this random variable x is in the range between xk and xk plus 1. We are defining, I am assuming that the value of x, the random variable x, is between the range xk and xk plus 1. So now how do I define the probability of this area? How do I define the probability? We all know that there is a term called as probability density function, which is a function of the probability of a random variable. Okay, so this is called as the probability density function, and its unit is probability per unit area. That is the unit of a PDF. That is the unit of probability density function, that is probability per unit area. And what is the area? Like I said, the area is in the range between xk and xk plus 1. And what is the area between xk and xk plus 1? We already found that. The area between xk and xk plus 1 is del xk, which means if you want to find the probability of x, all you need to do is multiply this probability per unit area, that is this PDF, with its area, which is del of xk. Therefore the probability is given by f of xk into del xk. This is the probability of a continuous random variable between the range xk and xk plus 1. Okay, this is f of xk is the probability per unit area, but how much area it is? It is del of xk. So therefore the probability is, you multiply this with unit area with the total area, which is equal to f of sk into del xk. This is the probability of a continuous random variable. Okay, so like I said I'm going to apply two concepts inside this equation, right? I'm going to apply two concepts. One concept is that I'm going to limit the value of del of x as tends to 0, so that I can basically convert this into a continuous random variable. And the second thing what I'm going to do is that I'm going to basically understand or basically define my probability as f of xk into del of xk. So by applying these two concepts, I can define the entropy of my continuous random variable x as h of x is equal to limit as del xk tends to 0, which is the same del x that you have applied over here. Okay, the limit factor. So I'm going to apply the limit over here, sigma, the same sigma over here. And here the values of k is infinite, right? Because the values of k is not discrete. That is, we know that the number of sample points between any 2 points of a continuous random variable is infinite. So therefore I'm going to say sigma for every value of k, the probability, the same probability, pk, instead of pk in discrete, I'm going to say f of xk del xk. This is the probability of a continuous time signal. So therefore it is sigma for every value of k, f of xk del xk log of 1 by again probability, which is f of xk del xk. So therefore, this is the equation for the entropy of a continuous signal, of a continuous random variable signal x. So h of x is equal to limit as del x tends to 0, sigma for every value of k, f of xk, del xk, log of 1 by f of xk, del xk. Okay. Now what I'm going to do is that I'm going to separate these two values. Okay, I'm going to separate these two functions into two different terms. So therefore, h of x is equal to limit as del x tends to 0, sigma for every value of k, f of xk, del xk, log of 1 by f of xk, plus the second one is over here, sigma for every value of k, f of xk, del xk, log of 1 by del xk, which I have split these two log functions into two different terms. Okay, that's what I did. Now what I'm going to do is that we know that the reciprocal of a log function is a negative. So therefore if I'm going to take the reciprocal of this plus becomes minus. So therefore h of x is equal to limit as del xk tends to 0, sigma for every value of k, f of xk, del xk, log of 1 by f of xk, minus sigma for every value of k, f of xk, del xk, log of del xk. So now what I'm going to do is that I'm going to apply my approximation to this equation. That is, we know that this approximation is going to become 0. So what will happen if this approximation del xk, that is the space between these 2 points, what happens between the space between these 2 sample points becomes 0, that is the distance becomes smaller and smaller, and finally both will become 1. Right, that's what happens if the distance becomes 0. Right, so the limit as del x tends to 0, 3 things will happen in this equation. One is that this xk plus 1, xk plus 2, xk plus 3, basically all sample points can be represented by a single value x, right? Because the space becomes very small that finally we will never be able to distinguish between two different sample points, because all of them will be same. So they are all represented by a single variable x. And basically we know that when del xk tends to 0, then f of xk into del xk becomes f of x dx, which is basically the definition of differentiation, right? That is, f of xk del xk becomes f of x dx. That is the second thing will happen. And the third thing will happen is that, since like I already told you that if you apply this approximation, you are basically converting the discrete random variable source into a continuous random variable source. Therefore, I am going to replace all by summation with integration. So therefore, the summation will be replaced by integration. These are the 3 things will happen when you apply the limit when del xk becomes 0. These are the 3 cases will happen. So I am going to apply these 3 concepts in this equation. Therefore, I will get h of x is equal to, instead of sigma, I have integral minus infinity to plus infinity f of x log of 1 by f of x dx, minus limit as del x tends to 0 log del xk into integral from minus infinity to plus infinity f of x dx. Okay. Now we know that one of the important property of a probability density function is that if you apply the integration of the probability density function of the entire area under the graph, if you apply the integration, you will get the value as 1. This is basically like saying that in the case of a discrete signal, we know that if you add the probabilities of all the discrete messages, you will get 1, right? Sigma k is equal to 1 to q, p k is equal to 1. In the same way, for continuous random variable, if you apply the integration of all the sample points in PDF, you will get the value as 1. Therefore, integral minus infinity plus infinity f of x dx is equal to 1. Therefore, this term will become 1. Therefore, h of x is equal to integral from minus infinity to plus infinity f of x log of 1 by f of x dx, minus limit as del x tends to 0 log of del x. Now this is where the problem comes. Look over here. When this del xk or this del x becomes 0, this will become log 0. Log 0 is basically undefined or infinite, or basically what it means is that this entropy becomes infinite. which means the entropy of a continuous random variable is infinite. I repeat, the entropy, the ordinary entropy, the normal entropy that you have studied before, the same entropy, if you are going to apply to a continuous time signal, you will definitely get the value as infinite, because log 0 is infinite. Since log 0 is infinite, this is infinite, therefore h of x is infinite, which means the entropy of a continuous signal is infinite, which is a bad news for us. This is the problem with the entropy of a continuous time signal. We don't have this problem in the discrete time signal, because in discrete time signal the number of messages are discrete, right? The number of messages are basically discrete. Between any two messages, the number of between any two transmitting of messages, the number of messages are actually always will be discrete. Either one message will be transmitted or two messages will be transmitted, like that. But here is not like that. Here the number of data or the amount of sample points between any two intervals, between any range of x is infinite. So therefore the entropy will naturally also become infinite, right? There are, if the it's just like simply saying that if the amount of data is infinite, then the amount of unknown variables is infinite. And we all know that the amount of unknown variables is what you call as entropy. So therefore the entropy will also become infinite. So that is why, that is the problem with this equation. That is, you cannot use a normal entropy if you want to define the entropy of a continuous random variable. That's the difficulty. So this difficulty can be removed, or it can be resolved if we consider the first term in this equation, that is this term. If I assume that this term is as my relative measure, and the second term as my reference, okay? That is, what I'm going to do is that I'm going to create a new equation. I'm going to define a new equation in which the second term is act as a reference, or I'm just simply going to ignore the second term. I'm just simply going to ignore the second term. I'm going to create a new equation in which the second term will simply act as a reference. Now, what is the meaning of the term reference, or why are we calling this as a reference? Is because when you, in all the entropies that you have studied before, what you are basically doing is you are basically finding the differences between two entropies. For example, if you want to take the equation for mutual information, I of xy is equal to h of x minus h of x by y, or h of y minus h of y by x. So in wherever you take the entropies, there'll always be this reference will always be there as a byproduct, which has no significance in your calculation. So what you're going to do is that I'm just simply going to, whichever equation entropy you take, there'll always be this reference is going to take. So what you're going to do is that you are just simply going to ignore that reference. We're just simply going to remove that reference, or pretend that it is not there. Just simply going to pretend that it is not there. So in that case, the equation now becomes h of x is equal to integral from minus infinity to plus infinity f of x log of 1 by f of x dx bits per sample. This is the new entropy of a continuous random variable, an entropy which does not have the reference. And since this entropy is not your actual entropy, this entropy, let me remind you that this entropy is not the exact entropy of a continuous time signal. The entropy of a continuous time signal is infinite. But since this is not an exact entropy, this entropy I'm giving the name as the differential entropy. So therefore, since this entropy is only a relative value and not an absolute value, we call this as a differential entropy. That is why we are using the term differential entropy, because this is not the absolute entropy of a continuous signal. This is the absolute entropy of a continuous signal, which is nothing but infinite. But we cannot apply this equation anywhere. This equation serves no purpose to us, and we still need an equation to define the entropy, and that is why we take this equation. that is h of x, that is the differential entropy of a continuous source x, is given by h of x is equal to integral from minus infinity to plus infinity f of x log of 1 by f of x dx bits per sample. This is how we define the entropy of a continuous random variable x, or a differential entropy. Now let's basically do a problem. So basically when we are doing the problem, we are going to apply this concept over here. Okay, that is, let's take this problem. Suppose x is a uniform random variable over the interval between 0 to 2, and its probability density function is defined as f of x is equal to 1 by 2 between 0 to 2. Yes, 0 less than or equal to x less than or equal to 2 is equal to 0 otherwise. So the question is, find the entropy of this continuous source. Okay, so we know that the entropy, this is the equation we are basically using, right? As we know that the entropy of x is defined as h of x is equal to integral from minus infinity to plus infinity f of x log of 1 by f of x dx. So what is f of x? F of x is already given over here, right? And also the range is between 0 to 2, because any other values other than that is equal to 0. So therefore this is integral from 0 to 2. F of x is 1 by 2. So this is 1 by 2 log of, and what is f of x again? 1 by 2. So 1 by 2 is 2 itself dx. This is the equation. Or in other words, this can also be written as 1 by 2 log 2 integral from 0 to 2 dx. Or in other words, this is nothing but 1 by 2 log 2, and integral of dx is x, so this is x from 0 to 2. Okay, so basically this is 1 by 2 log 2 into 2 minus 0, which is equal to 1 by 2 log 2, okay, into 2. This 2 and this 2 will cancel each other, so basically we have log 2, and since the base is also 2, the log 2 to the base 2 is nothing but 1. So this answer is 1 bit per sample. This is the entropy of this signal h of x. H of x is equal to 1 bit per sample. Okay, so basically this is what we do. We basically apply this equation. That's all. Okay, and so there are two things you need to understand when you're doing the problem. One is that you need to remember this equation, and the other thing is that you need to remember this concept. This concept over here, which is nothing but this concept, or this concept over here, f of x dx. Let's do the next question. Here the next question we have, find the entropy of the input x and the output y of an amplifier whose gain is equal to 4, and the probability density function of x is given by f of x is equal to 1 by 4 when between 0 less than or equal to x less than or equal to 4. Okay, and is equal to 0 otherwise. That's why it's not written over here. It's equal to 0, but only between 0 to 4 the value of f of x is equal to 1 by 4. Okay, how do I know this? Is because if you simply, like I said, if you, that's basically the meaning of probability density function. If you multiply the height, this is the height, and the width, you should get the area as equal to unity, right? So f of x is equal to 1 by 4, 0 less than or equal to 4 over the interval 0 to 4. Okay, so now let's do this question. So let's break this question into small pieces. Okay, first I'll read the first part. Find the entropy of the input x and output y of an amplifier whose gain is equal to 4, which means, this basically means y is equal to 4x. That's what it means. Okay, y is equal to 4x. Now what is the probability density function of x? Is f of x by 1 by 4, which means that h of x is equal to integral from minus infinity to plus infinity f of x log of 1 by f of x dx. Okay, and this f of x is also given as 1 by 4, and the limit is only between 0 to 4. Alright, and the rest of the value is equal to 0, so only between 0 to 4 the integral is 0 to 4. F of x is 1 by 4 log of 1 by 4 dx. Okay, which is basically, this becomes integral from 0 to 4 1 by 4 log 4 dx. Okay, or in other words, this will become integral from 0 to 4 this basically becomes 1 by 4 log 4 integral from 0 to 4 dx. Okay, or this will also become 1 by 4 log 4 into 4 minus log 4 into 4 minus 0. And what is log 4? Log 4 is equal to 2, right? Because the base is 2, so therefore log 4 is equal to 2. So therefore this is 2 bits per sample. This is the entropy of the input. Okay, they said to find the entropy of the input and the output. So this is the entropy of the input. H of x is equal to 2 bits per sample. Okay, h of x is equal to 2 bits per sample. Now I'm going to find the entropy of the output. So what is the equation for the output? This is the entropy as h of y is equal to integral from minus infinity to plus infinity f of y log of 1 by f of y dy. This is the equation for the entropy. But here the problem is we don't have the probability density function of the output. We have the probability density function of the input, but we don't have the probability density function of the output. Okay, so what I'm going to do is I need to find that equation. So we basically know that this is a linear equation, which means basically the probability between the input and the output is the same, right? Which means I can basically say that f of x dx is equal to f of y dy. Since the probability is equal to same, these two values are equal to each other. So what is f of x? F of x is 1 by 4. F of x is 1 by 4, and what is this? This is dx by, and let me say this is dx by dy, right? Dx by dy. So dx by dy is equal to f of y. So which means f of y is equal to 1 by 4 dx by dy. So how do you find the value of dx by dy? Simply, all you need to do is simply differentiate this equation, right? Simply differentiate this equation. We know that y is equal to 4x. So y is equal to 4x. So therefore, differentiating with respect to x, we get dy by dx is equal to 4, right? Differentiating this with respect to x, this will become dy by dx is equal to 4. Therefore, f of y is equal to f of x into dx by dy, which is equal to 1 by 4 into dy by dx is equal to 4. Therefore, dx by dy is equal to 1 by 4, which is equal to 1 by 16. So f of y is equal to 1 by 16. Okay. So now I found the value of f of y, which is 1 by 16. So basically, if this is 1 by 15, then the range of y, since f of y is equal to 1 by 16, then y is in the interval between 0 to 16, because we know that the area of a PDF must be equal to 1, right? The area of a probability density function is always equal to 1. So since we know the height, that is 1 by 16, then the breadth or the width must also be 16. So therefore this is the interval of y, 0 to 16. So which means basically this means that the equation for f of y is like this, as f of y is equal to 1 by 16 between 0 less than or equal to y less than or equal to 16, just like your f of x. Okay, f of x is equal to 0 otherwise. Over here also I'll just write it, okay, just for precision. Okay, alright. So this is equal to 1 by 16. So therefore, now I can find my h of y, right? Now I can find my h of y. So therefore, h of y is equal to integral from minus infinity to plus infinity f of y log of 1 by f of y dy, which is equal to, and what is integral? This is 0 to 16, and f of y is 1 by 16 log of 16 dy, which is equal to 1 by 16 log 16 integral 0 to 16 dy, which is equal to 1 by 16 log 16 into, and integral of dy is y from 0 to 16, which is equal to 1 by 16 log of 16 into 16 minus 0, which is 16 itself, which is nothing but log 16. Okay, log 16. So what is log 16 to the base 2? Log 16 to the base 2 is equal to 4, right? So this is nothing but 4 bits per sample. So which means therefore h of x is equal to 2 bits per sample, and h of y is equal to 4 bits per sample. Okay, this is the final answer. Now I want all of you to do the same question as a homework. Okay, and the homework and the question is, find the entropy of the input x and output y of an amplifier whose gain is equal to 4. Okay, same, whose gain is equal to 4, and the probability density function is given by f of x is equal to 1 by 2, 0 less than or equal to x less than or equal to 1 by 2 in over the interval 0 to 2. Okay, this is basically this. I want you all to do this as a homework. That is same question, but here the f of x is equal to 1 by 2 over the interval 0 to 2. Okay, that's the homework. And I want to do another homework in which basically here the gain is equal to 8. Okay, gain is equal to 8, and the PDF is the same PDF, and gain is equal to 8. That's your second homework. That is, find the entropy of input x and output y of an amplifier whose gain is equal to 8, and the probability density function of x is given by same, f of x is equal to 1 by 4 when 0 less than or equal to x less than or equal to 4 and is equal to 0 otherwise over the interval 0 to 4. Okay, that's your second homework. I want you all to do these two problems, and if you have any confusion, please contact me.